So we saw an example recently of a radical equation that we tried to solve, and it looked like we actually got a solution to it, but then we found out that the solution to the equation that we got didn't actually work in the original equation. So it's what mathematicians call extraneous. It's a solution that doesn't end up actually being a solution, despite the fact that we followed all the correct procedure. It's also a cautionary tale for always checking your answers. But I want to kind of quickly remind us of the work that we did, and then take a look at a graph that will convince us kind of what went wrong in the example we just looked at. So first, let's look back at the work to kind of recap what went wrong. So I'm talking here about the example in the middle, where the equation that we were solving is the square root of x minus 3 is equal to the square root of 3x plus 1. So this equation right there. So our first move was to square both sides. That got rid of both of the radicals and gave us this really simple linear equation with x's on both sides, mind you, but a simple linear equation nevertheless, that we ended up doing all the steps that we needed to do to get the x by itself. And we discovered x equals -2 actually balances this equation. The problem with x equals -2, though, is when we plug that solution back into our original equation, we end up with a problem. Specifically, when I plug -2 in for x, both of my square roots end up with negative numbers underneath them. So I get the square root of -5 on both sides. That's an issue because it means that there's no real number x, which makes both sides of our original equation come out to be the same real number. Now, both sides still come out to be the same non-real number. But if we're not sort of dealing with non-real numbers in the context of our course, then what are we to make of this result? So what I want to do is preview our next discussion about the graphs of radical functions by actually looking at the graphs of these two radical expressions, the square root of x minus 3 and the square root of 3x plus 1, and hopefully try to explain what just happened in the extraneous solution that we just got. All right, so what we're looking at on this screen is a set of graph axes. So it's the xy plane right here. This is the x-axis. There's the y-axis. And we're looking at the graphs of two different functions. On the one hand, we have the function g of x is equal to the square root of 3x plus 1. That's the graph here shown in orange. And on the other hand, we're looking at the graph of the function f of x equals the square root of x minus 3. That's the graph shown in blue. And so in our question that we just looked at, what we were trying to do was we were trying to solve the equation square root of x minus 3 is equal to the square root of 3x plus 1. And if that's what we're trying to do, remember this is the orange graph, or the expression that defines our orange graph, and there's the expression that defines our blue graph. What we're looking for is we're looking for a point of intersection. After all, that's what you're doing when you set one expression equal to another expression. We want to find out where these graphs cross. Where do they intercept each other? But if we look at these two graphs, it should be pretty clear just from their shapes that they don't. These two graphs never cross one another's path. This blue square root function and this orange square root function do not cross, let alone cross at the x value that we found when we applied a solution process to this equation that came up with a solution, a supposed solution of x equals -2, question mark, right? We found out when we plugged that back into our original equation that it didn't work. Well, why would that be the case? X equals -2 is over here on our graph. And if we look at all the set of points above and below x equals -2 on this graph, we're not finding anything. In other words, not only do these two graphs never intercept one another, they never intercept this vertical line at x equals -2. So why would that be the case? Well, that's the case because neither one of these functions is defined at x equals -2. If I plug a -2 in for x into the function g, I get the square root of 3 times -2 plus 1. That's the square root of -5. And because underneath the square root I have a negative number, this is not real. And therefore, -2 is not in the domain of this function, and so the graph never makes it over here. The graph never touches this vertical line. So there is no point on the graph of g in which x is equal to the square root of when x is equal to negative 2. The same thing is true of our other function as well. F of negative 2, square root of negative 2 minus 3. It's also the square root of negative 5. It's the same non-real number as g has when x is equal to negative 2, but again, it's still not real. And so the blue graph here also never touches the vertical line where x is equal to negative 2. So these two graphs never intersect. And specifically, they certainly don't intersect at the point where x is equal to negative 2. And the biggest reason for this is the reason that we call domain. To put a completely fine point on, terminological point on what we're doing here. X equals negative 2 does not belong to the domain of either function. It's not in the domain of f. It's not in the domain of g. And if it's not in the domain of either of those two functions, then it's certainly not going to be possible for those two functions to assume the same real value at the place where x is equal to negative 2. So this is what went wrong in the example that we just did. And again, the cautionary tale here is always check your answers when you're solving equations that involve radicals, because there's always an outside chance that your solution might not actually be a solution. It might be extraneous, as the example we just saw here.